if there's anyone here, but there are 3 people for regular, I guess. Okay. So the plan is that we'll have, I'm going to try and get through longitudinal static stability today. And then on Monday, we'll start with lateral directional. The remaining 2 hours of makeup have been scheduled for next Tuesday, 4 to 6 in this room. So I'm going to finish lateral directional static stability on Tuesday, and that will leave us 4 lectures for the remainder of the semester. So I'm going to do dynamic stability, look at the modes of flight during that time. Okay. All right, so let's try and finish static stability in longitudinal flight. So last time we looked at pitching moment, and we derived some expressions for the pitching moment derivatives. We're just going to write those expressions here for reference. CM0 that's CL0 wing fuselage CL alpha wing fuselage minus the contribution from the tail. And we have a couple other derivatives. And the important one is Cm delta E lecture. We said that we made an observation about whether or not we can fly stable in longitudinal flight without a horizontal tail, right? And so we said that if there is no horizontal tail, and this term goes away, and essentially what we need is in the wing fuselage combination, if you essentially have a flying wing, right? NASA has tested these concepts, and if you just have a projectile with a wing and fuselage combination, right? Like that. Then we are saying that we need Cm alpha negative, so that would require CG to be in front of XAC, the aerodynamic center of the body. Right? So this is where the aerodynamic center is. Again, like you need a reference to measure things, and things are being measured to the right? So this is XCG, and this is XAC. Then XCG minus XAC is negative, and this being positive, obviously, because you get increasing lift as the angle of attack is increased. Then Cm alpha is negative, and you get a stable configuration. This is purely from the point of view of stability, right? There is another concern, and that is whether or not you can trim the aircraft. Stability comes after trim, right? First of all, you have to be able to fly in trim, and then if a perturbation hits, you talk about stability. So purely from a stability perspective, you can fly without a horizontal tail by appropriately doing the weight distribution, right? Making sure that the nose is, most of the weight is near the nose than towards the rear end. So you can plot these things. So if you, for example, you can plot Cm versus alpha for 0 delta E and Cm versus alpha for 0 incidence, and you will have a nominal curve You know that Cm alpha needs to be negative, so that's the negative slope. And this may be for incidence angle of 0. Okay? So delta E is 0 for all the curves I'm going to show here. Now, two additional curves are shown here. And the question is, for this curve below the IH equal to 0 curve, is this IH less than 0 or IH greater than 0? Okay. So, see, the slopes are the same, right? The slopes are the same, so Cm alpha is the same for all these three curves because Cm alpha is the slope of these curves. So for this incidence angle, at the same angle of attack, you're getting a lower pitching moment. So do you think that that incidence angle is less than 0 or greater than 0? So this is the aircraft, right? This versus that. Right? So if the incidence angle is greater, you will get more lift, which will be a greater pitch down moment, which is an overall negative pitching moment. So pitching moment being low means that the incidence angle is positive. Right? So is greater than 0. And this is IH is less than 0. Okay. And similarly, for IH equal to 0, you may have curves like these for, say, delta E equal to 0. And this is going to be delta E greater than 0, delta E less than 0. Okay, for this, following the same set of arguments. Greater deflection, so delta E is defined positive, trailing edge down. Whereas incidence angle is defined positive, leading edge up. Okay. So, just looking at these expressions, especially this one, this expression leads to a bunch of very important concepts in longitudinal static stability. So the first thing that we're going to define based on that is something called a aerodynamic center of the aircraft. So we've looked at aerodynamic center of the horizontal tail, aerodynamic center of the wing fuselage combination, but then this expression will lead to the notion of aerodynamic center of the entire aircraft, okay, as a whole. And then that in turn will lead to the concept of the neutral point and then stability margin. So that's what we'll look at next, the aircraft aerodynamic center. And so the definition is identical to the definition of this or that, except that it's applied to the entire aircraft. So point along the V1 axis about which the pitching moment is independent of angle of attack. And this is that point for the entire aircraft, not just for the wing, fuselage, or the tail. Right? So from there, you see that you can use this expression to determine the point where the pitching moment is independent of angle of attack. Because wherever that happens, the sensitivity with respect to pitching moment, the angle of attack, is going to be sensitivity of Cm with respect to alpha is equal to, translate this to a statement about sensitivity. We are saying that the pitching moment doesn't change when angle of attack changes. So the pitching moment coefficient is insensitive, right, or 0. It's completely desensitized at that point, about that point. Okay. So we can talk about aerodynamic center of the aircraft, non-dimensionalized as, let's say, C over C, just like we had non-dimensionalized these guys with respect to the mean chord of the wing fuselage combination. And we can use this expression, Cm alpha, to determine XAC. Because Cm alpha is, by definition, the sensitivity of Cm with respect to alpha. And so we want to set that sensitivity to 0, which means we want to set this term to 0. So the question we'll be asking is, where can the CG be placed so that the pitching moment computed about that point, all the pitching moments are being computed about the CG, right? So what location of the CG will cause Cm alpha to be equal to 0? Because if at that point Cm alpha is 0, it means that the CG is located at the aerodynamic center of the aircraft. What location of CG causes Cm alpha to be 0? Because the Cm is computed about the CG. And if we are able to find that location, then we found the aerodynamic center of the entire aircraft. So it's pretty straightforward. Just set this expression to 0 and compute XCG. Okay. So call this star, U star, to get X bar CG star. That special CG location about which Cm alpha is 0 is equal to X bar AC. So you can do the algebra there, and that turns out to be X bar aerodynamic center of the wing and fuselage plus CL alpha H over CL alpha wing fuselage eta H SH over S aerodynamic center of the tail, downwash, whole divided by, this whole thing divided by 1 plus CL alpha H, CL alpha wing fuselage, H, okay. So I don't know how much experience you have in taking averages. If you have two numbers, A and B, what's the average of A and B? Well, that you're assuming that A and B both have equal weightage, right? Because essentially what you're saying is, so the reason I'm going off on that discussion is because I'm just going to show that it's the average of the aerodynamic center of the wing fuselage and the aerodynamic center of the horizontal tail, okay? So if you want to have two numbers, A and B, like you said, it's, you know, the common sense average is 1/2 A plus 1/2 B, right? Because you're giving equal weight half each to A and B. But you're not required to, right? In general, what you would do is, you can say the average is alpha A plus beta B. The only requirement would be that alpha plus beta equal 1. That's a unbiased average, right? So long as alpha and beta equal 1, you get an average in some sense with unequal weights to A and B. So that's what is happening here. See, the weight of the aerodynamic center of the wing fuselage is 1 times that, and the weight of the aerodynamic center of the horizontal tail is the rest of these coefficients. So it would be an average if the weights add up to 1, and you can do that by normalizing, add up the weights and divide the whole thing, right? 1, that's the weight of this, 1 plus that, and so the weights add up to 1. So it is an average aerodynamic center. And so that makes more sense, and this complicated expression, but what is actually happening? Just weighing the two aerodynamic centers, and somewhere in between is the aerodynamic center of the entire aircraft. Okay? So that's what we do here as well, if you note. The weight of A is 1, the weight of B is 1, so you add up all the weights, divide by 2. Same thing. Okay. And the other observation to make from here is, so ideally you want the aerodynamic center to be to be further back and the CG to be in front, right? You do realize this is not the actual location of the CG, right? If the CG were here, it would be at the aerodynamic center. That's the whole argument. What location of CG would cause Cm alpha to be equal to 0? We don't want Cm alpha equal to 0. We want it to be less than 0 for stability. But we are looking at this boundary, this kind of transition point from stability to instability. And as the CG starts moving backwards, it hits a point. It's this point where Cm alpha becomes 0. And then keeps going further back, it becomes positive, right? So to have more stability, where should we have this aerodynamic center? Further up or further aft? So suppose this is the aircraft, and here's the CG, the actual CG. And this is CG star, right? That I said if the CG were there, moving back, then Cm alpha would become 0. So for increased stability, you want CG star to be further back, right? Because there is more ways to go before the aircraft becomes unstable, right? If I am able to move this back, then I am increasing greater margin between where we are and where, if CG moved backwards, you know, maybe during flight the fuel is burning, who knows how the distribution is changing, right? Maybe the CG is moving back, or everyone decides to use the restroom together, right? Everyone moves to the back and something bad can happen, right? So there is more margin if CG star is further back. That makes sense? So how would you achieve that from here? Well, you can increase this term, and that can be done by moving the tail further back, as far back as possible, right? If the tail is farther away from the leading edge of the wing, then this term is greater and XAC is greater, so it's further back. Okay. And you can also show that if you increase the size of the tail, that also moves the AC for the raft. Although it's not that immediately clear because SH appears both here and there, right? So XAC, aerodynamic center of the tail, increase, or SH, increase, moves XAC aft, which is good from the point of view of stability, longitudinal static stability. And also by the same token, actually if SH works, then so should this, right? Because these two terms appear in the same way. So if you increase the camber so that you have the tail doesn't have a camber, so you know whatever way you wanna improve the CL alpha of the tail, you can pick a different airfoil which has a different CL alpha. A greater CL alpha will give more stability margin. Okay. So we haven't, I'm talking about stability margin, but I haven't formally introduced it yet. So we'll do that next. Okay. Any questions? Okay, so that takes care of the pitching moment. There is one more thing before we talk about these stability margins and neutral points and so forth. It's the consideration of thrust. And again, like this is something you just look at, but it's never actually used in the equations because the thrust is assumed to be aligned with the B1 axis, but in general it may not be aligned. So here's the B1 axis of the aircraft. Right? And suppose this is the thrust line. That's where the engine is. Okay. So you see there will be some pitching moment. Right? If this is where the CG is, so there will be some pitching moment like that about the CG. Because the thrust is not acting along B1. So if this is the displacement or the displacement of the thrust vector, then the pitching moment is due to thrust is minus T dt. So again, this term is there, and we'll look at this briefly when we're talking about trim. But if you want to get more details about this, look at section 5.3.4 in the book chapter that I've uploaded on carbon. Okay? I'm not going to go into any more detail than that. All right. Let us look at longitudinal static stability, and we already know the answer here. What we've done so far is we looked at, if you remember, a couple of lectures ago, we started looking at drag, and we looked at lift. Then we've just now finished looking at the pitching moment, and very briefly, the thrust. Right? So we have taken into account all the forces and moments that go into determination of longitudinal static stability. So now we can start making some statements about whether or not the aircraft is stable. And before you can do that, there is a little bit more detail that you need to talk about. So one of the students had mentioned something about stick fixed and stick free stability, okay, in a past lecture. So what we will do is we will assume stick fixed stability throughout, and I'll quickly tell you what that means. So, in order to talk about stick free and stick fixed stability, you need to look at what are called reversible and irreversible flight control systems. Okay? So, flight control surfaces. And what this is, a reversible flight control surface is one which is direct. Have any of you ever been in a cockpit? Okay, so if you get inside the cockpit of a small aircraft like a Cessna or a Saratoga, you will see that you obviously have a stick that controls the elevator deflection. And how do they control the rudder? The pedals. Right? So pedals control the rudder. So those are the actual physical, where you give the physical input as a pilot. Right? So in a reversible system, the stick, whenever I say stick now, I mean the elevator control. Right? And pedals, this is rudder. Are directly, and by directly I mean physically, mechanically, however you want to interpret it, are directly connected to the control surfaces. So the elevator stick is directly connected to the elevator using things like push rods and cables and pulleys and stuff. Okay? So here's the stick, right? And there's a push rod, there's some connection, transfer of effort, and then you have a system here that's directly connected to the elevator. So why is this called reversible? So if you pull on the stick, the elevator will move. If you get down from the aircraft, walk to the back and move the elevator up and down manually with your hand, the stick will move. So it's reversible in that sense. Okay? That you can control the stick using the elevator and the elevator using the stick. Okay? So that's another way of saying that there is no hydraulics anywhere in the line, along this line of connection. Right? No hydraulics. Now during flight, no one is going to hang from the back of the aircraft, causing your stick to go out of control. No human being that is, but there's obviously going to be flow, right, and perturbations. So perturbations are going to hit the elevator like a gust, and they can cause, you're flying the aircraft manually. These small aircraft, maybe there is no advanced flight control system, like no autopilot. So you are physically flying the aircraft, and you have to hold the stick tight. right? So that the air flow doesn't cause the elevator to move and then with it the stick to move around. Right? So that's why there is this concept of stick fixed for reversible systems, because there is no way to cause the elevator perturbations to just happen on their own accord because of perturbations. There's no hydraulics to prevent that from happening. So if the pilot is taking a break somewhere and a perturbation hits, then everything's going to change. So for reversible systems only, there is the notion of stick fixed and stick free stability. Okay, so here pilot holds stick during perturbations. And here pilot is absent. And the elevator just floats up or down depending on what kind of perturbation is hitting the table. So, back in the day, maybe a couple, 2-3 decades ago, even now, the pilots talk a lot about handling qualities, right, of aircraft. This is kind of what they mean. How does the stick feel in your hand? Exactly, literally, that's what it is when you're flying. And of course, if you're flying at high speed, then you can imagine that it will take a lot of effort from the pilot to hold the stick in place, right? Because it gets more stiff because you're flying faster. The perturbation is gonna, it will be harder for you to hold it to. So it does take a lot of physical effort in the absence of an irreversible system, in the absence of hydraulics, in the absence of automated flight control systems. And there are aircraft like that you can just fly using your senses and your muscular power, literally. Okay? So there is a limitation to how big the aircraft can become on a reversible system, because it's just not humanly possible to control it after a point. Okay? So these are therefore only very limited to small aircraft, and we're going to assume that we are living we are living in this domain, where you have irreversible flight control systems or surfaces, where even if you let the stick, you take a break, get coffee or something, the perturbation on the elevator will not cause the stick to start moving. Okay? And the elevator is going to stay fixed. And so this is always stick fixed. So there is a nice picture in the chapter, in the textbook, that kind of illustrates all this. I'm going to try and draw that here. So here's trim. Here's the horizontal tail, and maybe that's the B1 axis, and this is B infinity. So this is trim. A stick fixed perturbation looks like this. Nothing changes, because the pilot is holding the stick fixed even when the perturbation hits. So V infinity, this was V infinity trim, this has changed because of the perturbation and the angle of attack. This is alpha trim, this is alpha trim plus delta alpha. Angle of attack has increased, that's a perturbation. But this is still the same, because the pilot is holding the stick fixed. So this is stick fixed perturbation. Whereas if you have a stick free perturbation, then because of the increased angle of attack, the elevator is going to float up. This is a stick-free perturbation. So all the equilibrium conditions, everything will change, right? The elevator deflection has changed. And so, we need to look at a different set of equations to handle the stick-free case. And in any case, like I said, the stick-free case only applies to systems without hydraulics, which there are only a limited number of now. And most of the aircraft flight control surfaces are irreversible. So we'll consider stick-fixed from this point on. Okay? So we'll look at stick-fixed longitudinal static stability. All right. So, what are the conditions? What are we seeking here? We are, of course, looking at only the longitudinal motion, and the objectives. There are two objectives. One, achieve trim, right? And two, be stable to perturbations. And we are looking only at the pitching moment, perturbations and angle of attack. Remember, this is all cruise. Right? So everything is cruise. The reference is important. So trim, when I say trim can be anything in general without context. It could be pull-up trim, a coordinated trim, a turn trim, and so on. We are looking at cruise trim. So, from the point of view of these expressions here, the pitching moment expressions, what's the trim condition? Cm is equal to 0, right? No pitching moment. Well, what you actually have is that the pitching moment is equal to 0, but that is equivalent to this. Because pitching moment is Cm Qs C. And stability, well, we want static stability. And we know the condition for this. Cm alpha is less than 0. Right? So these are the two objectives of longitudinal flight. Assuming, of course, that everything is balanced along the x-axis, right? You have enough thrust to balance drag and so on. So that is being assumed. Assuming thrust is approximately equal to drag and lift is approximately equal to weight. We have seen this before. We looked at trim in much greater detail than this rather simplistic analysis. That leaves only, given thrust and drag, lift, that leaves us with the pitching moment, and those are the conditions that we need. Alright, so let us look at the trim first. Do a moment balance. on the center of gravity. So this is the same analysis that we did for the pitching moment. You have the lift of the wing fuselage times the moment arm. So this is xcg minus xac wing fuselage plus the pure moment about the aerodynamic center of the wing fuselage minus a pitch down moment from the horizontal tail. And I'm just going to throw in this thrust moment as well for just a little. We'll throw it out soon. So that's the total moment. We want this to be equal to 0. This is for trim. And so the question that we are asking right now is, how much lift is needed from the tail in order to deliver trim? Okay. And the reason I'm asking this question is, at the end of the last lecture and early on today, I said that we don't really need a tail to fly stable. But then I immediately qualified that by saying that, but there's no guarantee about trim. Can we achieve trim without a horizontal tail? That's the question that we are trying to address right now. Well, we'll look at that from here. So let's solve for LH, and you get that the lift needed from the horizontal tail is lift from the wing fuselage combination So assuming that you do have a tail, this is how much lift is needed from it in order to achieve trim. Okay. Now, like I said, we're going to set this to be approximately 0. And look at a conventional aircraft, which means that you have an aft tail, right? So aft tail means xch minus xcg is equal to is greater than 0. The tail is behind the CG. That's normal. LWF, that's the lift from the wing fuselage combination. Obviously this is greater than 0. Even for non-conventional aircraft you need positive lift. So this is positive, this is positive, positive camber wing. Wings will usually have a positive camber, right? For more lift. What can you say about this term, the aerodynamic, the moment, pure moment about the aerodynamic center of the wing fuselage combination? For a wing with positive camber, do you know the sign of this term? Anyone from aerodynamics? So I don't know why, but this is negative. You can ask someone in your aerodynamics class. Okay. But for positive camber wing fuselage combination, this term will be negative. The reason we are doing this is we want to see what kind of lift is needed from the tail. Is it a positive lift, or do you actually need a negative lift to trim the aircraft? Okay, so let's figure this out then. The denominator is positive because the wing is, the tail is aft. This is positive this is negative. Okay? So essentially it depends on the sign of this term. So given this conventional aircraft, now case 1, CG forward of wing fuselage. So CG is in front of the aerodynamic center of wing fuselage. So that this is negative. Meaning that the wing fuselage itself is statically stable. The CG is in front of the aerodynamic center of the wing fuselage. So positive times a negative. This is negative, this is negative, and this is positive. So in this case, for trim, you need negative lift from the tail. So here's a contradiction. We said that if you have a statically stable wing fuselage, meaning the CG is in front, right? So the wing fuselage is statically stable, but you can't trim it without having a negative lift coming from way behind the tail, right? So wing fuselage only, XACWF aft of XCG is statically stable but can't be trimmed. Okay. And in case 2, you know where that discussion will go, right? Case 2 is CG is aft of the aerodynamic center, so CG is behind the aerodynamic center. So maybe you can trim it because this is positive, this is positive, this is negative, right? So somewhere there is some CG location that will give you zero requirement from the tail. But that's a meaningless discussion because you can trim it, but it's statically unstable because the CG is behind the aerodynamic center, right? So you can't have both. You can either be statically stable, you can trim it, you can trim it, but you can't be statically stable without a horizontal tail. Okay. Case 2, trim, yes, possible, but static stability, no. So how is NASA flying their tailless aircraft? There's something up there obviously, so it is flying. So you always go back to the assumptions, right? This is what we call a conventional aircraft. Obviously that's not a conventional aircraft. One simple thing you can change here is change the camber of the wing. If you have to have just a wing and a fuselage combination, then you can't have a positive camber. Okay? So let's see what happens if you have negative camber. So case 2, or change up the assumptions, new assumptions. You still have a, suppose you have a aft tail. We're going to gradually shrink it down to 0. That's the idea. See if that's possible. Of course, the wing from the fuselage and the lift from the wing fuselage is always going to be positive. But 3 have negative camber. So that the aerodynamic center wing fuselage moment is is greater than 0. Okay. And I'm going to be looking at only one case, okay, where CG is forward of AC, because this is useless. This is unstable. Right? If CG is behind the aerodynamic center, that case is not worth much, because even though if you can get trim, you can't fly in a stable manner. Right? So be very careful about this distinction between trim and stability. These are very fundamental concepts that you should be very clear about. Trim is just achieving nominal. But stability is when you subject that nominal to a real life scenario where there will be perturbations. If there were no perturbations, trim is sufficient, necessary and sufficient. But in the presence of perturbations, trim is necessary but not sufficient. Alright, so case 1, where you have CG forward of aerodynamic center of the wing fuselage. So come back here, CG is forward, so this is negative, right? This is positive, so this thing is negative, and this now is positive because of the change up of the camber. So I can move the CG around, right, so that I get a 0 here, and I don't need any contribution of lift from the horizontal tail. So we can shrink it down to 0 size. So CG forward of this implies static stability is automatic, but also implies that CG can be placed to get LH equal to 0, i.e. fly tailless. So now we're going to go back to a conventional aircraft with a tail, right? This was an interesting discussion just because it helped you play around with these equations and read some physics into these math relationships. But now moving forward, we're going to assume that we have a conventional aircraft and there is a finite size tail, and this is the lift you will need from that tail in order to fly trim in a stable manner. Okay, so if you have a tail, the next question is, that's the lift you need, and the amount of lift needed is going to change depending on a changed trim. You fly at a different speed, fly at a different angle of attack. So what setting of the elevator will give you this required tail contribution of lift? By the way, we just saw that when we do have a tail, we need negative lift from the horizontal tail, right? So what setting of the elevator will give us this negative lift? So the trim elevator computation can be again done by the basic trim equation. And the basic trim equation is that Cm equals 0. Right? So remember that Cm is Cm0 plus Cm alpha Cm delta E plus Cm IH. So if you know your trim angle of attack, then you can use this equation to determine the trim elevator deflection. That's going to be minus Cm0 minus Cm alpha So expect questions like this in the test. This is a fixed quantity, right? Pretty much. You are not going to change the incidence of the entire tail. Right? The Cm0 is a constant. This is a constant too. So look at this term, dependence of the trim elevator deflection on the angle of attack. If you are stable, then this is negative, right? If you're flying at a positive angle of attack, then this is positive. There's another negative here, so the numerator is positive. What about Cm delta E? Can you tell me through arguments what sign does a conventional aircraft have for Cm delta E? How would you go about making arguments? Well, first interpret this, right? By definition, this is dCm d delta E, right? That's the definition of Cm delta E. Sensitivity of the pitching moment coefficient to elevator deflection, which can be coarsely thought of as replace the partial with a finite sized change. Now you are in a position to determine its sign. So think of a positive change in delta E. Right? What's a positive change in delta E? Delta is the elevator deflection. Positive is defined as trailing edge down. So you are here. Suppose you go from here to there. This is a positive delta E, right? To that. So trailing edge went further down. This is delta E is greater than 0. What do you think will happen to the pitching moment when you do this change? When you increase the deflection, this is an even more cambered surface. Lift is going to increase, which is going to give a pitching down moment, right? Because it's the tail. The aircraft is here. Right? It's going to increase the lift here. So that there will be a pitch down moment about the CG. So delta Cm will be, the change in pitching moment will be negative. Correct? So for a positive change in elevator deflection, you got out of the aircraft a negative pitching moment. So the signs are opposite, which means this is less than 0 for a conventional aircraft. right, with the tail in the back. Because if the tail was in the front, then this lift will give a pitch up moment. That's a canard, right? In a canard configuration. So this is negative. So delta E trim is negative, right? Negative, negative, positive, negative. And that makes perfect sense. The elevator needs to be like this for flying trim. And that's what we said, we need negative lift. That's consistent. Okay, so I'm just going to try and summarize this. What we've done so far in the first hour. Trim plus static stability for conventional aircraft, and by this I mean aft tail, positive camber, wing. What else do I have? Okay, trim requires LH less than 0. A negative lift, i.e. trailing edge needs to be up. Right? You need to fly like this. For trim only. And for static stability, all we need is that Cm alpha be less than 0. And a necessary condition is that XCG is XAC wing fuselage is aft of, well, this is not a necessary condition, I'm sorry, this is a sufficient condition. A sufficient condition is that the aerodynamic center of wing fuselage is aft of the behind the CG. So the wing fuselage itself is stable, adding a tail only augments the stability. Therefore, this is sufficient to say that the conventional aircraft with the tail has CG aft of, or aerodynamic center wing fuselage aft of CG. Okay, and so the trim plus static stability for tailless we need negative camber on wing for what? Trim or static stability? The camber. Think about it. Static stability just requires placement of CG with respect to aerodynamic center. It doesn't care about what the shape is. Camber is the shape, right? So the camber part came from trim. And we still need XCG for static stability. Okay. That's good, or we break? Good. Okay. Alright, so that leads to the discussion of aerodynamic center. Remember, we had this discussion briefly a little while ago, aerodynamic center of the entire aircraft, and we found a location for it in terms of that special CG location that would cause Cm alpha to be 0. So we're going to look at that and extend the concept of aerodynamic center of the aircraft to something called a stability margin. Aerodynamic center of the entire aircraft. Okay, this is, we're going to revisit. We just derived an expression for it a little while ago. Okay, so let us compute the aerodynamic pitching moment, or the total pitching moment about the center of gravity on the aircraft. So this is the CG, obviously. Suppose this is the aerodynamic center of the aircraft. So the cool thing about having aerodynamic center is that that's where the total lift acts through, right? That point. You can decompose the lift to be the total lift from the aircraft. I don't have to worry about decomposing this into LWF and LH anymore. We don't care, because we know the aerodynamic center of the entire aircraft, and that's the point through which the total lift on the aircraft acts, plus a pure moment, MAC. So, and that's it, right? The picture gets cleaned up big time, because I don't have to break this up into wing and tail and whatnot. That is it. Assuming that the drag is acting along B1 and the thrust is acting along B1. Small angle of attack. Right? Therefore, the computation of the moment now becomes much simpler. If you look at this, now assume some datum, right? Maybe we are measuring still from the center, from the leading edge of the wing. So this is XCG and this is XAC. Okay? So from this picture, the moment on the aircraft is lift times xcg minus xac plus the pure moment. And so divide throughout by QSC bar to non-dimensionalize this, and we get that Cm about the Cg, of course, so with that the pitching moment is Cl, that's the total lift coefficient, and then this C goes inside the bracket to not dimensionalize the lengths, x bar Cg minus x bar AC plus Cm AC. That's a very handy expression. Because now I can differentiate with respect to alpha, d alpha of both left and right hand sides, and we get that Cm alpha is equal to Cl alpha times from here right? What can you tell me about the very last term there? Just from first principles, definitions. What is the variation of the pitching moment about the center of mass? About the aerodynamic center with respect to alpha. By definition of the aerodynamic center, this must be 0, right? That's the cool thing about this special point, is that it doesn't vary with alpha. And so we get this handy expression, an alternate expression. We already have an expression right here, right? Cm alpha is that. And that is great. That's great for design, right? Because it tells me what size of a tail do I need. Right? But this is great too, because it's much simpler. It's the overall lift coefficient, the overall aerodynamic center. And so these are two identical expressions, but give two very different perspectives about the Cm alpha, which is critical obviously to longitudinal static stability. Right? We want this to be less than 0, and we want this to be less than 0. So from here, it's trivial to see that this aircraft is statically stable, because xcg is in front of xac, so this is negative. Right? Identical on LHA's left hand side, but very different perspectives on the right hand side, RHA's. Okay. Yeah.
How did you get rid of the one just erased right now? The partial Cm AC and the partial.
That's the pure moment that's independent of the angle of attack. That's the special thing about the aerodynamic center. It's a special point about which the pitching moment does not depend on the angle of attack. So when I take a partial with respect to alpha, it's desensitized, right? And so from here, I'm just going to say this again, static stability demands that xcg be front of XAC. It does not mean that XCG needs to be in front of XAC wing fuselage. Right? XAC is a weighted average of the XAC of the wing fuselage and the XAC of the tail. Right? This is not the same as XAC wing fuselage. It's the overall aerodynamic center of the aircraft. Be very careful there. Okay, so from here we get, directly from here we get the notion of something called a neutral point. So like I said, that gives you one very high resolution perspective of CM alpha, right? Because it goes into the details about, oh, if the tail is of this size and it has this dynamic pressure ratio and so on, this is where the downwash and so on, you get this CM alpha. And here, this is a much high-level bird's eye view, right? If here's the aircraft with an overall aerodynamic center given by that, then you have the following CM alpha. Great. So this bird's eye view perspective can be used to determine something called a neutral point. Okay. And a neutral point is defined in a way you would expect it to be defined. It's where you have neutral stability, right? Location of CG where aircraft hits neutral stability, which is the boundary, right? It's neither stable nor unstable, i.e. CM alpha is equal to 0. And as you can see, we get that same expression that we got early on, right? That XCG equal to XAC is equal to X neutral point. This is not the actual CG again, that special CG location about which if the CG were there, the aircraft would have neutral stability. Okay. If the CG is here and here's the neutral point, then you have a ways to go before you hit neutral stability. And for that simple reason, that you do have a ways to go, there is some margin, right? It's called, this distance is called the static margin. Is the gap between CG and aerodynamic center, which is the location of the neutral point. Okay. So formally, the static margin Sm is defined as XAC minus XCG is the definition. So that CM alpha can be written as CL alpha minus CL alpha times static margin. So if you have positive static margin, the aircraft is statically stable. That makes sense. Okay. So look, static margin is defined as the negative of this term, right? So that's what I just used here. Going from here, there, we define Cm alpha in a very high level view, bird's eye view, as the overall Cl alpha times the static margin, negative. So positive static margin, obviously this is positive, means you have Cm alpha negative, which is a statically stable aircraft. So one of the, if you had a course, so when I was in my undergrad school, we had experiments in flight mechanics course, and that's when we would get inside, small aircraft and do some experiments, take measurements, get data and plot some, straight line curves and determine the static margin or CL alpha, Cm delta E, and so on. Remember the table I drew the other day on the board? What kind of experiment would you need to set up? If you had an actual aircraft, take it up in the air, get your measurement sensors out, make measurements, and do some simple hand calculations. Okay? So we have to be careful what we ate for lunch before we went up in the air, because those were small aircraft and you can feel everything inside those aircraft, all the jittering, and we would try to get the aircraft close to stall, and the most god-awful thing I heard, like it was the most scary thing I heard actually, was getting close to stall, an alarm starts going off. That you're getting close, you're stalling, and everyone was freaking out inside the aircraft. The pilot was calm, but we were all carrying buckets up there. So anyway, the reason I'm talking about all this is because determination of this neutral point is a very important thing, right? You need to know what's that danger point in your aircraft. Because if the CG wanders to its aft, you're going to become unstable, right? So a very important flight experiment is to determine of the neutral point, or essentially determining the aerodynamic center of the aircraft, because that's the location of the CG where you have neutral stability. Okay, so we're going to connect two things, and this will be the last thing I'll do today, I promise. Then we can break. On Monday we'll do maneuvering point, and then on Tuesday again, next Tuesday we'll do lateral directional stability, and after that we'll move on to dynamic stability. Okay, so the first thing to note is that the static margin, when the static margin becomes zero, you have your CG located exactly at the aerodynamic center, right? Great. So the static margin is minus Cm alpha over Cl alpha. This is observation 1. But then I can play around with this a little bit. If I expand this, this is dCm d alpha and dCn d alpha. Right? From first principles, from the definition of these coefficients. So of course this is dCm dCl. Right? So I can write this as minus Cm Cl, if you may. Introduce new notation. The variation is sensitivity of Cm with respect to Cl. Great. So this is the first observation. And this is going to be useful because CL can be measured in flight. If you're cruising, then QSCL is equal to weight. Lift is equal to weight. So CL is equal to weight over QS, which means that if you know the weight, if you know the speed of flight, which is a simple instrument on the panel in front of you, and what else? You know S, of course, because that will come with the handbook of the aircraft, right? But also if you know the altitude at which you're flying, because that's the density, you know the dynamic pressure, and therefore you know CL. So it's a very easy thing to compute, right? And this is the total CL of the aircraft. Great. The next thing that is easy to note is the elevator deflection. Right? It's an actual instrument that you can put an instrument back there, a sensor, that keeps track of what the actual deflection is of the elevator. Right? So we're going to exploit that fact. So to do that, I'm going to revisit that trim expression that we had. I derived this a moment ago. So if you flip your pages a little bit, this is what we had. CM0 plus IH, CM IH over CM delta E. Okay. Plus or minus alpha trim, CM alpha, CM delta E. Okay. So this is easy to measure. So I'm going to play with this a little bit now. CL is CL0 plus alpha CL alpha. Right? And of course, alpha CM alpha, like we did here, is alpha CM dCM d alpha, which is alpha dCM dCl dCl d alpha. This chain rule. And so this becomes alpha CM CL times CL alpha. So we get a nice connection here, look. We have CL alpha CM alpha, but that we have just found is equal to this. Okay? So I'm going to make that substitution, and for simplification we're going to call this constant term delta E0. So delta E trim is delta E0 minus alpha CM alpha is alpha CM CL times CL alpha over CM delta E. It's just some algebra here, right? Now, finally, I'm going to bring, I don't like this CL alpha. We're going to bring in CL. So, this becomes delta E0 minus Cm Cl over Cm delta E alpha Cl alpha, which is Cl minus Cl0. Okay, so essentially I've used this here. Okay. So we have this constant, another constant term, Cl0, 0. So I'm going to absorb that into here, and we get that delta E trim is delta E0. You're going to call this star, the Cl0 term absorbed in there, minus CmCl times Cl over Cm delta E. Okay. Okay. And the final step is to differentiate this with respect to Cl, del Cl. So this goes away, that's constant, and we get that the partial of the elevator deflection with respect to Cl is equal to minus CmCl over Cm delta E. That's the expression that we've been chasing. The reason we have been chasing this expression is that now both this and this are easily measurable. We already said that Cl can be obtained from this data here. Right? This is obtainable from W, S, V infinity and altitude. And this is directly measurable from sensor. So, the observation, key observation is the following. So the observation 2, right? What's observation 1? That the static margin is equal to this. Here. Right? So, two measurable entities on the left hand side, partial d delta E, Cl is equal to static margin over some constant, I don't care. This. And this is the equation that we need for design of the flight experiment. So what are we going to do? We're going to fly the airplane at a bunch of different the left hand side is completely measurable, right? So we can fly the airplane at a bunch of different, fill in the blank, at a bunch of different CL. Note the required elevator deflection to achieve trim, right? And get that curve. So this is what we're going to do. On the x-axis, we have CL. On the y-axis, we have delta E. Right? We're going to fly the airplane at a bunch of different CL. And we're going to measure what elevator deflection was needed. right? And we're going to get the curve. The slope of this curve is what? Look at that expression. The slope of this curve is this, right? The derivative of delta A with respect to CL. Okay. So we're going to get the slope to be some constant SM1 over K. Whatever your current static margin is, wherever you're flying, right? Over Cm delta A. That's the slope. We got this number for some location of the CG. Now change the location of the CG, make it move back. Right? So when the CG moves back, the static, what happens to the static margin? It shrinks. Right? So the slope shrinks. Right? So do this all over. This is for CG number 1 or static margin number 1. Land, go back and land after flying at all these different angles, lift coefficients. So this entire experiment can be done in one flight, right? Just vary the speed. The lift coefficient will change and get all those points. Then go back and land, change the CG location and fly again at a bunch of different CLs, right? And if you move the CG back, then we get a curve like this, right? Because the slope has gone down. It's a gentler slope, right? So, static margin number 2. And the CG is in this direction. As we go along this direction of the experiment, CG is moving in which direction? Aft. Moving. Sorry. Yeah, aft. Aft means back. Long lecture. Aft. Moving backwards. What will happen when the CG is located at the neutral point? The static margin is 0 and you will get bleep, right? You will be able to fly at all speeds at the same elevator deflection, right? And whenever that happens, you know that your CG, which is measurable, right? You know that with placement of the weighing scales, you can measure where the CG of the aircraft is. So for this flight configuration, wherever that CG is, you found the neutral point. Okay. Now there's a practical issue. Are you going to send undergraduate students on that airplane which is zero static margin? No, right? So we're going to stop here. Maybe do 2 or 3 more and stop here. Okay, don't go any further up. That's not safe. There is no static stability in the aircraft. So there's one more step involved in. You can get this neutral point by extrapolation. Okay, so measure the slope. Now on the x-axis, put the location of the xCG. Okay, and pick up this line. That was your first flight condition. Measure the slope, right, of that curve. Negative. They're all negative slopes. So you get something. And you moved back, so the slope went down. And you moved further back, the slope went down. And then you stopped, because it was not safe after that. Right? So just extend the line after that point. Okay? And you have a location of the neutral point. Okay, does that make sense? Right? Okay, I have just one more topic. I'm not going to do that now. We're all kind of drooping down a little bit. So I'm going to do maneuvering point and maneuvering flight. Then, just like we have a neutral point, we have a maneuvering point, and we'll do that on Monday. I'm going to finish that on Monday. Like I said, Tuesday we'll do lateral directional stability. So all of lateral directional stability will be squished into one lecture on that 2-hour lecture on Tuesday. Wednesday, Friday, Monday, and Wednesday. 4 lectures for short period and for quite a long. Great, thank you for coming. Happy Thanksgiving.